This is chapter 9, part 2 of Moments of Inertia. This is lecture 19, and in this lecture, I just want to go over a few examples, a couple more examples of how to calculate moments of inertia. Now, most of the time, moments of inertia are used in building and structures. Not to say that's the only use, but in this case, the examples I have are examples of what would be beams used for construction. So if you have a large structure you're putting up, then you may use a certain type of a beam. And so each time the beam's used, the designer isn't going to necessarily calculate the moment of inertia by hand. Rather, there are charts and tables that you can look up the basic information based on the shape. So it turns out that in this first example, we're looking at an S310 by 47.3, and that's the S stands for the shape of the beam, and it comes from published standards. So for example, this beam here, the S stands for S shapes or American Standard shapes. The 310 represents the nominal depth. So the nominal depth would essentially be the depth is referred to oftentimes as the height. And so in the terms of beams, depth means the distance from the top of the beam to the bottom of the beam. And so then the number after that, the 47.3 in the metric system, since this is millimeters, represents the kilograms per meter of how, so that's how much this beam actually weighs. So if we were using the English system, it would be pounds per foot or pounds per yard, depending on what you're looking at. And then the depth would be in inches. So just because it says 310 doesn't mean it's exactly 310 millimeters. In some cases, that might be slight variation of that. But that's where that comes from. So on this one, because of that reason, we can look up the properties of that beam in a book in terms of what its moment of inertia is and what its cross-sectional area is. And in this case, we have two 20 millimeter steel plates that we've attached to the top and the bottom to add extra rigidity to the beam, and which is a whole other story. And when you take, if you take C204, you'll look at this in much more detail. So we want to find essentially what are the moment of inertia about the respective X and Y centroids. Now we can see that this is symmetrical, so there's not going to be a change in the X and Y bar. It's just essentially going to lie along the existing X and Y axis, which is center. So this is your textbook here, and this is what I was talking about in terms of the shapes. And you can see if you open up to page 501, depending on the book you have, well, it should be the edition I recommended. You notice that S American Standard, there's that and that. And so, let's see if I can get this to focus a little better. You can see that we have the, in our example, we have the S310. And so that's going to be on this page, sorry. So here we have the S310 by 47.3. So we look at the depth. Notice that the depth is 305, so it's not exactly 310. Just like the next one down says S250, it's 254. This is 150, it's actually 152. So again, there's a variation. So the depth again is the height from the top to the bottom. And then if you keep going, you'll notice that depending on the axis you're looking at, if you're looking at the XX axis as defined here, then it gives you what is the moment of inertia about the x-axis in times 10 to the 6 in millimeters to the 4th. And it also gives you what's called the radius of gyration, which we'll explain shortly. And then if we go a little bit over, we see that if we're going about the y-axis, it also gives us those values. So this is a nice way to be able to look these things up so that you don't have to recalculate or reinvent the wheel every time you're doing a problem like this. Okay, so let's look at this one. So we have here, I've drawn this. So we have our structure, and I've pulled the values off of the table. So the area, 610 millimeters squared. IX, about the centroid. So I put the bar there. So IX and IY are respective 90.3, 3.88. And the area of the plate, so this area is of this I-beam, the plate is 3,200 or 160 times 20. So we know that if we want the total IX, that's going to equal IX of the SI beam plus 2 times IX of the plate. So I put the line over the S because the beam doesn't require the parallel axis there. The beam is on its central axis. So if we calculate this, we can just, we know that for the plate, it's just going to be, let's go ahead and determine what it is for just the plate. So because we already know this value, this is the same as up here, it's 90.3. So we know we're going to get 90.3 times 10 to the 6, and then plus 2 times. Now for this, since it's a rectangle, it's going to be 1/12 BH cubed. So 1/12, and then 160 is the base, and the height is 20. All right, so that's that part. But because the plate is down here and our axis of rotation is up here, we have to use the parallel axis there to get from here to there. So our distance on this example so here's our distance. So we know that our depth in this case was 310. Yeah. So we know that half of that is going to be 150, 305 over 2. Did I get that? Sorry about that. Check something on the sheet. Sorry about that. The depth actually on this one, even though it says 310, the actual depth is 305. So we know that from here down there, it's going to be half of that, or 305 over 2. So half of that is going to be 152.5, and then half of this is going to be 10. So we know that for our AD squared term, it's going to be plus 3,200 millimeters squared. So that's the area of this, and then times 152.5 plus 10 squared, or 162.5. So again, we have the IX plus AD squared because the plate's not. So that's that, and we put our bracket on the end, and then we do the rigorous math, and we get 84.667 times 10 to the 6 millimeters to the 4th. So if you remember your powers, you know that to convert from millimeters to meters, you multiply by 10 to the minus 12. So since it's the power of 4, there's a difference of 3, it's 4 times 3 is 12. So this could be 84 times 10 to the minus 6 if you want it in meters, but we'll leave it in millimeters. So let's see. Now we have that. I apologize, I didn't add in, that's this part. I deviate from my notes. That's this part, and then we still have to add in 90.3 times 10. So our total number, our IX for this, gives us a total of 260 because the 84 is multiplied by 2 also. So it gives us 260 times 10 to the 6 millimeters to the 4. And that's our answer right there. Now there's this thing called the radius of gyration, and it's the root mean square of the distance from the rotation point to the area. And the way you calculate it is you have kx squared is simply equal to Ix over total area. So it's a fairly easy calculation. So if we go to say kx equals the square root of 260 times 10 to the 6 millimeters to the 4th and divide that by the total area, which would be 610 plus 2 times that, there's 2 plates, the total area ends up being 12,410 millimeters squared. And so we end up with the square root of millimeters squared, so we get an answer in millimeters. And this equals 144.6 millimeters. And this is also a very common number that you'll use if it takes you to a 4. All right. Okay, so now if we want to do the same thing with the plate, then the plate actually is fairly straightforward for about the y-axis, because then, actually I saw this big space on here. So if we think about it, if we rotate and we find the moment of inertia about the y-axis, then we don't have to use 80 squared because the centroid of all shapes, this, and this, all lie along the axis of rotation. So if that's the case, then it's just simply Iy equals Iy of the S-beam plus 2 times Iy of the plate. So in that case, it's just going to be Iy equals, and we know that from the table we got this for it around the y-axis, so it's just 3.88 times 10 to the 6 millimeters to the 4th, and then plus 2 times. In this case, we're just going to use the standard 112, and now our base is 20, and our height is 160. And so we add this all together, we get 117.53 times 10 to the 6th. Probably should make 10 to the 7th, but I like the powers of 6, 9, 12, so forth, millimeters to the 4th. All right, so that's that about the y. So it's different, which makes sense, quite a bit smaller than it would be about the x. And that makes sense given how much material you have that's away from the axis of rotation compared to the y-axis. And then if we want the radius of gyration, that's just going to be 17.53 times 10 to the 6 divided by total area 12,410 square root, and in that case we get radius of gyration to be 37.6 millimeters. Again, this is something you'll see much more if you take CE classes. Okay, so that's that. I have one more example I want to show you. And it'll be here. So this one's just a little different. In this example, what we're doing is we have a plate that has been connected and welded to 2 C shapes. And so going back to our trusty book, the C shapes look like a C, as you can notice, and that's these things down here, C250 by 22.8. So If I look up the C250 again, the depth actually on this is 254. So again, not quite the same, with a weight of 37.8 kilo, or I should say a mass of 37.8 kilograms per meter. So we'll go ahead and work that one. Go. So here we have our C channel, and then we have a plate. So we're given that the plate is 10 by 375 and the C channel. So we want to find IX and IY. And we're given the distance of the two C channels is 200 millimeters. So how do we go about doing that? So for one, when we look up the C channel, we find that its area, we have its X bar here, 16.1, but we should also write down its area is 2890. Let me do that real quick. So there's the new information. We have A, IX, IY for the C channel, and the total area would be 2 times the area because there's 2 C channels, and then 2 times the area of these plates, 10 by 375. So we get this for our total area, which we'll use later. So then if we want to find IX, then we know that's just going to equal to 2, and that's going to be times 2 times the 28.0 times 10 to the 6, right? Because we have these two, and we're going about the x-axis. So we're at the center of the x-axis. So for these channels, so we don't need to use the parallel axis theorem. And then we're going to add in what we get with the plates, and this is very similar to what the problem we just did. So with this, then we're going to have the 2, and then we're going to have to put in 1/12 375 base times height, and then we're going to have to add to that the 80 squared, which is 3750, the area, and then the distance 132. So the distance being from here, there, plus 5. And so that comes out to be 132 millimeters based on the depth of the plate. And so I think I said that the depth was for this one 254. Yeah. So that's where we get the 132. So we had 254, so it's 125, 127 plus 5. So that's where that comes from, 127 plus 5. There it is written there. So that's squared and bracket. So we end up this whole value, IX bar equal to 186.7 times 10 to the 6 millimeters to the 4th. And if we take that and divide it by our total area here, then we can find our radius of gyration. So turns out the radius of gyration ends up being 118.6, which you can check. All right, just by taking the IX divided by total area and then taking the square root. So then we just need to do IY. So now IY will have also a parallel axis because this here is not on the axis of rotation, but the plate's center is. So we kind of reverse them in terms of what's what. So IY, again, is equal to IY of the channel plus IY of the plate. And so for the channel, we have 2 times, and then we have 0.945 times 10 to the 6, which is just the published value for that about the y-axis. And then our 80 squared term is the area, 2890 millimeters squared. And then our distance, And so we know that for our distance, it's going to be 200 divided by half. So we know it's 100 going to here. And then from here out to here is 16.1. So we have 100 plus 16.1. That gets us from here out to the centroid of that. Okay, that's where that comes from. So this is going to be times 116.1 squared. All right, there we go. That's in millimeters. Sorry, hard to read. Squared. So we come out, we end up with everything added together. We end up with 79.8 times 10 to the 6 millimeters to the fourth. So that's for the channel. And then for the plate ends up being 1/12 pH cubed, of course. So, or it equals 2 times 1/12, 10 times 375, that's height. So that gives us 43.9 times 10 to the 6. And that's per plate. So this is my notes. So what I should have done is probably not had the 2 in there. So that's what that is. So effectively, our IY is going to be equal to 79.8 plus 43.9 plus 43.9. That gives me 167.7. And that's all times 10 to 6 millimeters to the fourth. And sorry about that. So 79.8, 43, 43. So 43 is for each plate. That's for that. And then lastly, we have, if we want our radius of gyration, that's just going to be this value over the total area. And that's going to give me 112.4 millimeters. All right, and that's it. So those two examples are very similar. That's as far as we're going to go with moment of inertia. And hopefully this is helpful, but otherwise this next homework, it's only 4 problems due on Monday, and then we'll be back on track. We'll start talking about chapter 6 on Monday, and hopefully have something up over the weekend, but that will be the majority of what we'll do in the next couple of weeks. And then we'll talk about friction, and then we'll be done. So quarter goes quick. Stay safe and have a good weekend.